So I'm going to introduce the basics of quantum information. So really the goal is to build a common vocabulary so we can talk about things and they can serve to the lectures that come in next. So actually I'm going to introduce two systems to describe quantum information. So one will be based on state vectors and unitary operators. And the other one is based on density matrices and quantum channels. Okay, so the first system we will introduce in the first lecture here, and then it's also going to be sufficient for describing most of the quantum algorithms, which will be the main focus for the second lecture.
Reduce that?
Can I move it away? Oh, okay, that looks better. And then, all right, so for the second system, the density matrix formalism, this is going to be the topic for the third lecture. So these definitions and tools will be essential in building, let's say, quantum crypto and analyzing security of cryptographic protocols, either classical or quantum. Okay, so most of the materials will be rather standard, and many of you in the audience probably are already familiar with and know probably better than I do. That said, there's one distinction than a standard introduction to quantum computing, which would be that we'll consciously think about the impact to cryptography along the way. Okay, so I do have a request to make. So whenever we introduce or encounter a unique quantum feature, either it's a limitation or a power of quantum information, I want you to think in the back of your mind how this might impact crypto. Would that break something? Would that change the model? Would it change some analysis? And then how to fix the break, how to change the model, how to come up with a new model, and then more excitingly, can we come up with new constructions based on the new features of quantum information? Okay, so really think from both perspectives of the attackers and also a designer. All right. Okay. I think that's all I want to say in the beginning, and let's get to it. So let me directly jump into quantum circuit model. So I guess everybody here is familiar with Boolean circuits, which is a computational model. Each wire represents a bit, and then we can apply Boolean gates. So the time goes from left to right. As the time progresses, we apply some gates, and in the end, we read out some output, and hopefully it can compute something meaningful. And then quantum mechanics tells us there's a new type of computation that's possible, which will be identified with quantum circuit model, and this is going to be governed by the laws of quantum physics. So there are going to be new objects. For example, we need to talk about quantum bits or qubits, and also we need to talk about what kind of quantum operations we can apply. Okay, so this brings us to the basic quantum formalism. Okay, so first of all, what is a qubit? So we're going to consider a quantum system, which I'm going to call a register X. Okay, and the state of X is going to be described by a two-dimensional vector with complex entries. And the only condition is it has to be normalized, meaning the norm, the length, is going to be 1. So if you compare this to the classical setting, So think about we flip a coin, which lands on heads with probability, say, P0. Now we can also use a two-dimensional vector to represent that. Right? So we can write down P0, P1. And the condition is P0, P1 sum to 1, and they are both non-negative. So as you can see, the quantum bit here is really just the extended probabilistic state, which means instead of talking about probabilities, we talk about amplitudes. So these numbers, alpha and beta, they are called amplitudes. And then the normalization condition, instead of using the one norm, as in probability theory, we use two norm. Okay, so this is a quantum bit. So again, it's a unit vector respect to the Euclidean length in C2. All right, now there is a complex way to write down these vectors, which is called the Dirac notation. So we're going to take a bracket here and then insert a bar, split it into two pieces. The right part is a kit. This is going to be used to represent a column vector, and the left part, this bar, is going to represent a row vector. So for example, two possible states of a quantum bit, of a qubit, would be 1, 0, 0, 1, which we're going to denote by kit 0, kit 1, respectively. Okay, so you can think of these two spatial states as the two classical bits, 0 and 1. You can identify with that. And if we plot these two states, K0, K1, in this 2D plane, you can notice that they actually form a basis. Okay? So that means any other quantum state, alpha, beta, can be written as a linear combination of 0 and 1. So let's say it's here. And then usually we're going to use some Greek letter in the Dirac notation, say this is a state psi, or you also see a state phi in this way. So again, this is just a linear combination of 0, 1, but physicists, they call this quantum superposition. I mean, mathematicians will be like, what the heck is superposition, right? And I think they're justified to roll their eyes. But we will see. When we come to computation, this does make a difference. Okay? And just to be complete, so I said this bar will be used to denote row vectors. So that means bar 0 will be the row vector 1, 0, and bar 1 will be the row vector 0, 1. Okay, so let's look at a special quantum state here. So again, recall if you have a classical fair coin, then we can write it as this vector 1/2, 1/2. So this is a classical coin. And then there's an analog of a quantum bit, which if we have 1 over square root 2. As the two amplitudes there, so we can call this a quantum coin. So this state will be denoting as, come back. Let me zoom it in a little. So we'll call this kit plus, okay? And since you can have, arbitrary complex amplitudes, in particular, you can have negative amplitudes. So another one, you can imagine there's 1 over square root 2 and negative 1 over square root 2. And this state, we're going to be called it ket minus. As you might have observed, these two states form another basis for the qubit space. Okay, so another convenience of the Dirac notation is that inner product will become really easy to write down. For example, if I want to take the inner product of the vector 1, 0, then it's just going to be the row vector k0 multiplied with the column vector k0, and this goes to 1. And on the other hand, if we have k0 and k1, the inner product, well, obviously it's going to be 0 because they are orthogonal to each other. So this is very convenient. Okay, so this is about a qubit, right? So we have the basic unit to encode information. But then we want to ask what kind of operations we can perform on we can apply to a qubit. And then quantum mechanics tells us they have to be linear operations that preserve length. And then you'll realize from linear algebra, that gives us just one choice, unitary operators. So if you write down the matrix for a unitary operator, it's going to satisfy the condition that U dagger multiplied with U gives us identity. Okay, so here U dagger is the complex conjugate of this matrix U. So you take the transpose and then take the complex conjugate. So for example, if we have this 2 by 2 matrix A, B, C, D, the dagger will be A, D, C, B, and then the complex conjugate. And just in case it's not clear, the complex conjugate for a composite number is x minus yi. Okay, so these unitary operators will be what we can apply to a qubit. So here are a few examples. Well, the simplest one, at least I can think of, is doing nothing, which is, applying identity to a qubit. So this is a matrix representation for identity, and then in the circuit model, we're going to use this box, write identity inside. Okay, so clearly, for any input qubit, it just outputs the same. So the way I describe it is I just describe what this operator does to this computation, to this basis k0 and k1, because that determines what it will do for another arbitrary qubit by linearity. Okay, so this is identity, and then another interesting gate, well, maybe not so interesting, is the X gate, X operator. So the matrix form is this, and you can probably tell by matrix multiplication in your mind, and you can figure out this is actually just flipping the bit. So it maps k0 to k1, and maps k1 to k0. Okay, so this is, classically we call this the NOT gate, and in quantum mechanics we call it bit flip. And then there are a few others, like the Z gate. Let me just write it down. So Z gate is kind of interesting. It keeps k0 unchanged, but then it introduces a negative sign on k1. So we call this a phase flip. Okay, so this -1, or in general, in quantum physics, we can introduce e to the I theta, which is just a complex number on the unit circle. We call it a phase. So Z gate flips the sign. We call it a phase flip. And another gate, the Y gate, the Y operator, let me write down the matrix, and you can observe that this is actually just identity, not identity, sorry. I times xz. So it's the product of xz plus this phase I. Okay, so it basically has the combined effect of x and z. So given 0, it maps to I1. Given 1, it gets mapped to negative I0. Okay, so this for basic operations, or the 4 gates, we call them polygates on a single qubit. And they're going to be useful in some basic quantum crypto protocols, or in general in quantum information. And maybe one interesting property I should mention is, the squared all goes to identity. Okay, so you can verify what I said, that this operator does what I told you, just by doing your matrix multiplication. Okay, so far so good. Any questions so far? All right, cool. Let's move forward. So the unitary operators are what we can apply to a qubit, but eventually, we probably want to read out some information that might be useful to us. So that takes us to a special operation in quantum mechanics, which is called merriment. Okay, so you want to observe a qubit. And in the quantum circuit model, I'm going to denote it using this kind of meter symbol. So when we observe a qubit, when we apply a merriment on qubit, what happens is, well, it's slightly complicated. Suppose we have an input, we have a state psi. Okay? So we're going to see 2 possibilities when we observe it. We're going to either see 0 or 1. Okay? And we're going to see them with different probabilities. So what's your guess about the probabilities? Well, they better be proportional to the amplitudes, but we know the amplitudes are complex numbers, they are not probabilities. So the natural choice is to just take the amplitude squared, or rather the magnitude squared, and that's going to be the corresponding probability for observing either 0 or 1. Okay, not too surprising. But what's interesting is, once you observe it, once you do this merriment, the state will collapse. At least that's what physics call it. That means after the merriment, if you see a 0, then your posterior state will become K0. On the other hand, in the other case, if you observe 1, then the posterior state will be K1. Okay, so let me show you a visual picture. So this is K0, this is K1, and then this is the state psi. As you can see, this is basically just projecting this vector psi under this basis, K0 and K1, and you see each one with probability proportional to the magnitude squared, and importantly, afterwards, it will collapse to either K0 or K1. Okay? So this is pretty much the quantum theory on a single qubit. We have introduced what a qubit is and the operations. We can apply a unitary and do a merriment. And also, I should mention, we can also prepare the initial state in K0 or K1. Okay? But so far, we've been talking about a single qubit. That's probably not so exciting. We probably need to move on to bigger systems. So let's talk about multi-qubit systems. All right, so let's start with 2 qubits. So suppose I have 2 qubits here. Let me call them X and Y. And suppose their states are psi and phi, respectively. So how do we put together? What's the state to describe this composite system? Well, it's going to be determined by their tensor product. So for example, if we have x being in case 0 and and y in case 0 as well, then this joint system will be k0 tensor product case 0, and if you just write it out, this is going to be, so how do we do tensor product? You just take the entry from the first matrix and then make a copy of the second one. Okay, so this gives us 1, 0, 0, 0. Okay, and we give it a shorthand notation. We call it ket 0, 0. And similarly, you can figure out a few other states. For example, ket 0, 1 is just k0 tensor ket 1, and that's going to be 0, 1, 0, 0. So let me just write down two more. Okay, as you can already observe, these 4 states will be a basis for all 2-qubit states. So an arbitrary 2-qubit state can be written just as a linear combination of these 4. And the only condition here is they have to be normalized, meaning the Euclidean norm has to be 1. So alpha squared plus beta squared plus gamma squared plus delta squared. This has to be 1. Okay. And the space for these 2 qubits will be, 2-dimensional complex space tensor with C2. That's isomorphic to C4. So the dimension grows to 4. Okay, and we can generalize from here to arbitrary n-qubit states. Okay, so you can already imagine a basis for n-qubit state, which is going to be, you take, for each qubit, you have these 2 basis states, and then you take all combinations of the bases and take their tensor product. So you have 0 tensor to the n, 0 tensor n minus 1, and tensor 1, all the way to ket 1 tensor n times. Okay, and the shorthand notation will be just 0 to the n. This will be 0 n minus 1, 1, and 1 to the n. So what are these states? What are these vectors? Well, suppose you have realized these are just the standard basis for a 2 to the n dimensional space. Okay, so this will be just 1, 0, 0, 0, and the last one will be 0, 1. Okay, so they form a standard basis in C2 tensor n, which is C to the 2 to the n. So I want you to observe here that, again, this dimension grows exponentially with the number of qubits. And this is a different feature than classical bits. Okay? All right, so now we have the description for n qubits. Now we want to talk about what kind of operations we can apply in general for n qubits. Well, they followed pretty much the same rule. So we'll have unitary operators on n qubits. So again, these unitary operators will have dimension 2 to the n times 2 to the n, such that the same condition holds. Okay, and then we can perform a measurement on n qubits. So suppose the n qubit state on the x row, the amplitude is alpha x. Then if we measure it, we're going to see x with probability proportional to alpha x magnitude squared. And then after the merriment, the state will collapse to ket x. So it will collapse to one of the computational basis states. Oh, sorry, I didn't mention that. So these are the standard bases, and in quantum information, we also call them the computational bases. Maybe I can write it down. Okay. All right, so let's see a few examples, and do interrupt me if there's anything unclear.
Can I ask about the measurement operator? So is this, do you think of it as a linear operator on some space, or do you think of it as a random operator?
So the question is, do I think of the merriment as a linear operator or just a random operator? I would think of it as a random operator. So just, following this rule. You see it, you see some classical label, classical outcome with certain probability, and then the state collapses to one of the standard basis states. All right. Okay, so let's think about this vector here, 1 over square root 2, 0, 0, 1 over square root 2. So I want to ask you, can you write this? So this is supposed to be a 2-qubit state. Can you write it as the tensor product of 2 single qubit states? I'll wait for 3 seconds and somebody can tell me. How many say yes? Okay, then I'll take the answer no. And that's correct. You cannot express this as a tensor product of 2 single qubit states. And this actually illustrates what physics call entanglement. And this particular state, let me denote it as phi plus. This is the famous EPR pair. So in Dirac notation, it's just 1 over square root 2, ket 0, 0 plus ket 1, 1. And there are a few others. Let me forget about the normalization and just write down the important piece. So I have phi plus and also phi minus, and I can also introduce psi plus minus, which will be 0, 1 plus minus 1, 0. So these 4 states are particularly interesting. For one thing, they form a basis. For another, it's going to be interesting in quantum information in a lot of different places. So they are actually called the Bell states. Okay. So again, this entanglement, from mathematical perspective, there's nothing surprising. But that just means the 2 systems are correlated in some way. You can also have joint distributions which are totally correlated. For example, you flip a coin and then you copy that coin. Right? Then you have a 2-dimensional vector, probabilistic vector, which you cannot written as the tensor product of 2 2-dimensional vectors. This is not surprising, but physically, such entanglement, such quantum correlation is really puzzling and also exciting. It can be used for many information processing tasks, and we'll see some examples. Okay, so this is a special 2-qubit state, and then let's talk about a 2-qubit operation. So this is the famous controlled NOT gate. So I have 2 qubits. The top one is going to be a control qubit, and the bottom one is going to be the target. Okay. So what this operation does is it's going to flip the target if and only if the control was 1. So sometimes this is also drawn as this. You have the XOR on the target. So let me write down the kind of the truth table for this operator. Just following this rule here. if I have input K00, then nothing changes. Same for K01. But if my control bit becomes 1, then it's going to flip the target. So this becomes 1, 1. And on input 1, 1, it becomes 1, 0. Okay, so this is a very interesting gate. Now I want you to figure out, what if I apply the control NOT, or C NOT for short, if I apply this to this special input state, Kate plus as the control, just to remind you, this is 1 over square root 2, Kate 0 plus Kate 1. And then the target being 0 will be the output state here. Let me draw this a little nicer. Yeah, that's better. Can somebody tell what the output state will be? Just using linearity. What's that?
How will you denote it? Cat plus plus?
It's not going to be Cat plus plus. It's yes. So let's say, so I have Cat plus on the control, so I write it as K0 plus K1, and then tensor with K0 as the target. And then I want to apply C naught, right? Now, by linearity, this is going to be C naught applied to each component, so I have C naught applied to Cat 0, 0, and then C naught applied to Cat 1, 0. Okay, and then we can just read out from the truth table here, or just follow the rule. If the control is 0, it doesn't change it. If the control was 1, it flips the bit. So this is what we're going to get. Well, I mean, modulo the normalization 1 over square root 2. So do you recognize what this is? Oh, it's right here. This is the EPR pair. So this is how you prepare the EPR pair. Okay, using one C naught gate. All right, so let me pause for a second. Are there any questions so far? And I need to take some water.
I just what you said, this is equivalent to what? The last, your conclusion is pointing back to something?
Oh, yeah, so this output state here is just going to be exactly this EPR pair, this entangled state. Any other questions? Okay, if not, we can move on to something slightly more interesting. So let's talk about some basic quantum information processing tasks. And when I say basic, they are basic. So first of all, let's think about something you might hope to be able to do, such as, distinguishing two states. All right. So suppose I give you, I prepare a register. I prepare in one of the two possible states. It's either going to be Ket plus or Ket minus. And I want you to tell apart which one I prepared. Can you do it? Yeah, John is saying yes, for sure. Well, I mean, there's a linear operator we can apply that can help us distinguish these two states. And the whole goal for this exercise is to introduce that spatial operator. So let me introduce this operator. I denote it as H. This is going to be the Hadamard gate. So in matrix form, it's pretty simple. And then this is the circuit symbol for it. So what this Hadamard does is, I mean, you can, again, work out the matrix multiplication. If the input is K0, it's going to map it to K plus. And if the input is K1, then it maps to K minus. Okay? And in fact, if you just apply it one more time, you get back to identity. So let's actually see what happens here. So suppose I start with K0, I apply a Hadamard, then I get K0 and plus K1, so that's the plus state. Now, suppose I want to apply Hadamard again, then by linearity, I just need to apply Hadamard to K0 and K1 and then combine them, right? So let's say if I apply Hadamard to K0, I get K0 plus K1. And then if I apply Hadamard to K1, I've got the minus state, which is K0 minus K1. Now something interesting is happening here. If we combine these four terms, you can see these two, they will cancel. So we're only left with.
Do you need that matrix or no?
Sorry, say again?
Do you have the right matrix? There's a minus sign.
Oh, yeah, good point. Otherwise, it's not going to be unitary. Yes, thank you. All right, so we can see if we think of this as a computational graph, or so if you think of it as a computational graph, there are 4 branches in the end. 2 of them will cancel. So this is an indicator that in quantum computation, there's something we might be able to take advantage of, to reinforce the possibly correct paths that can lead us to the correct answer for some computation. And then somehow control the other paths, the incorrect paths, for them to cancel out. Okay, so this is what sometimes people call constructive interference. So this is already an indicator for something that might be possible. Okay, but now that I have introduced this case, let's come back to the original question. I want to distinguish these 2 states. Now with Hadamard, it becomes simple, right? So if I give you this register, you just apply Hadamard. And then you just measure in the computational basis. You will see either K0 or K1. And you will know initially which one I prepared. Okay? So this Hadamard can help us, solve this problem. But a follow-up question, can we distinguish K0 versus K plus? What would you say?
What do you mean by distinguish?
So I prepare a quantum register, which is in one of the 2 states, either K0 or K plus. I hand the register to you. I want you to tell which one I prepared.
What am I allowed to do?
Anything.
Well, if I can think of, those orbitals that different.
You can apply any unitary operation. You can measure them, and all physically admissible operation you can do in your lab. Yeah. Well, the answer is you probably have sensed it. We're not going to be able to perfectly distinguish these 2 states, K0 and K plus. So the difference between this pair and the previous K plus, K minus pair is that K plus, K minus, the formal basis, they're orthogonal to each other. So the inner product is 0. But K0 and K plus, they're not orthogonal. And in general, non-orthogonal quantum states cannot be perfectly distinguished. So let me write down this claim. Okay, so this actually leads us to the next interesting feature of quantum information. All right, so when we think about classical information, we always take it for granted that if I write down a few bits, you can tag them and make as many copies as you want. Can we do that for quantum information? Well, so we can imagine. So what we want here is a copy machine, right? A quantum copy machine, which I denote as a unitary. So the goal is to, I take an input vector, input state psi, and possibly with some additional work qubit. And then I want to produce 2 copies of psi. Is this possible? Well, the answer, unfortunately, is no, we cannot do it in general for unknown states. So one immediate way to see some difficulties that, suppose this unitary U does exist, and then if we apply it to 0, then we better produce K0, K0. And if we apply it to K1, if it works correctly, then it will produce K1, K1, right? Now, if I want to copy K plus, which is a linear combination of K0 and K1, what we would want is 2 copies of K plus, right? But this machine, this copy machine, it has to follow linearity. Then what actually happens is it's going to produce, let me write it here. So again, by linearity, we just need to apply U to each component. So this produces 0, 0, and 1, 1, the EPR pair, right? This is not going to be 2 copies of K plus. So this already indicates there's some problem. And in general, if we consider 2 arbitrary input states that we want to copy, suppose it does it correctly. We produce 2 copies of psi, and another state, we get 2 copies of phi. Now since, again, unitary operator preserves length, that means, so if you take the inner product for the left-hand side and the right-hand side, they have to be the same. So let me rewrite it. And this is another convenience of the Dirac notation. So this is what we're going to end up with if you take the inner product for both the left-hand side and the right-hand side. And how can this identity hold? Well, again, suppose in the beginning, we know psi and phi are not the same. Then this must mean that the 2 states have a 0 inner product, meaning they're orthogonal, right? So this implies this machine is only going to work for orthogonal states. And in fact, there is a deep connection between, whether we can distinguish the states, and on the other hand, if we can copy them. Okay, but again, the general message here is an unknown quantum state cannot be copied in general. And this is the famous no cloning theorem. And a very bizarre feature of quantum information. So again, what I showed you, this is not a complete formal proof, but just give you some idea why this doesn't seem likely. Okay? Any questions about the non-cloning theorem? Okay, very good. Now, moving on to the next task, which is teleportation. And here the basic idea is, what you want to do is to send a qubit via some classical channel. Suppose we don't have quantum channel connecting two parties. I want to send a qubit to another person, but I can only send classical bits. How can I do it? Well, the most kind of naive way is to send the amplitude. And then you realize immediately, suppose I have this, the quantum state alpha 0, the qubit alpha k0, beta k1, then maybe I can write down alpha in decimals. And then you realize immediately, this is not going to be a good idea, because alpha can be arbitrary complex number, and we only have bounded precision. And the bigger problem is, suppose, what if I don't know the state? What if Alice doesn't know what psi is? Can she still send this qubit to Bob through classical communication? Well, turns out entanglement can be really helpful here. So for any qubit state psi, Alice just need to communicate two classical bits if they pre-share a EPR pair. So I call it a E-bit, entangled bit. So if they pre-share a EPR pair, then Alice just need to send two classical bits, and then Bob can recover arbitrary psi. Okay, and here's the particle. So we have Alice and Bob. Imagine they're physically separated, but somehow they pre-share a EPR pair. So these two qubits they form an EPR pair. And then Alice has some arbitrary input state psi here that she wants to send to Bob. Now, what happens is Alice just needs to apply a C0 and then a Hadamard on the first qubit, and then perform a merriment. Okay, so I hope this circuit symbol still makes sense. And after the merriment, Alice will get these two bits, A and B. And then she just needs to send these two bits to Bob. And what's interesting is that after this merriment, on Bob's side, this state is already going to be something very similar to psi, the initial state, up to some bit flip or phase flip. And that can be corrected using these two classical bits. Sorry, I don't know how to do it properly. Here we go, that's better. So Bob will just apply a controlled bit flip, which is controlled by the bit B, and then another controlled phase flip according to the bit A. And then this state here is going to be exactly psi, which is Alice's initial state. It's kind of like magic. So we're now going to analyze this particle, because we're going to analyze some circuits which look similar. And after that, you should be able to figure this out on your own. But this teleportation, so this is called Condom Interpolation, and this is actually very useful, not just as a tool for sending information, but as an analytical tool in proving security in quantum cryptography. You'll see later on. Yeah.
So what do you mean by saying that this C is going to be alpha 0 plus beta 1? Is to say that if both repairs on this last wire, if you happen to have a copy of, say, a bracket 0 or something like this.
Okay.
That this C, on that last wire, that new state that he gets after this procedure will behave like bracket 0.
Yes, the second part is correct. So initially, so this is the same, okay, I should make it clear. This is the same physical register sitting there. Initially, it's part of the EPR pair. Right? So initially, this guy and this guy, they form an EPR pair. And then Bob just waits until he receives the two classical bits and then perform this controlled bit flip or phase flip on this register. And then the resulting state will be exactly psi.
But this symbology means to say that whatever operation Bobs wants to do in the future, they behave on this wire as if that wire were exactly alpha 0.
Exactly. Yeah, it is that state.
It has a certain, still some ghost part of it that lives in Alice's space, right? It's still entangled with something.
No. It's totally decoupled with Alice's systems. So this is like a fresh, if you wish, a fresh copy. Like it is this psi state on its own. Yeah, that's the kind of maybe counterintuitive part. But if you work out the analysis, you will see it's a psi sitting on that register. You can use, you can treat it just as you have prepared it, from fresh. Okay. All right. So now we've seen a few basic tasks, and let me just make a brief remark. About universal quantum gate set. Okay, so we've been using this quantum circuit model for a while, but it's important to note that we can have a finite set of quantum gates that we can use to approximate any unitary operation, and this is indeed possible. And let me just give you one example. So on one qubit, on a single qubit, any unitary operator you want to do, you can construct using just these two gates. One is the Hadamard, the other one is the T gate, which is in matrix form 1, 0, 0, e to the I pi over 4. Okay, so it just introduces a phase if the qubit is 1. So this is a universal gate on single qubit operations. And in fact, you can approximate any unitary up to some precision, which is efficient, meaning it scales polylog in terms of the inverse of the precision you want. And that's the famous Solovay-Kitaev theorem. I'm not going to state the formal theorem. It's not necessary for this lecture. All right. Now, if you just add, C naught to this set, then this becomes a universal gate set for arbitrary unitaries, any number of qubits. Okay, yeah, that's pretty neat. And then an important family of quantum circuits or quantum operators is the so-called Clifford operators. Again, this will be useful in quantum cryptography. And these are going to be the circuits or operators you can generate by composing Hadamard and C0 and another gate called the S gate, which is just introducing a phase I on gate 1. So the Clifford circuits, they're often kind of a test bed for quantum information protocols. If you want to start from somewhere, you come up with a scheme that works for Clifford operators. Okay, so this is just a brief comment I want to make on universality of quantum gates. All right, let me pause for a second. Any questions? Yeah. I'm reading from right to left. C0. Thank you. Any other questions?
So the T gate basically gives you the ability to rotate one of the qubits by 45 degrees, right?
The T gate?
Yeah.
No, T gate doesn't rotate. It's a phase. Like you introduce this e to the I pi over 4 on gate 1. Yeah.
So yeah, gives them the phase.
Yeah.
So I'm having a hard time seeing how that can ever be used to induce a shift smaller than that. Like how would you get pi over 8, a shift to pi over 8?
Does somebody know the answer? I don't know that on top of my head.
Okay, but you're saying that it can be done?
Yeah, yes. Anything else? All right, okay. Now, I think that finishes the introduction part, and we're gonna get to quantum algorithms, which is kind of my favorite. Okay, and to introduce quantum algorithms, we first need to discuss a new model for computation, which is the black box or the query model. So we need to talk about black box functions and query model. So let me start with a classical black box. So basically this just means I have a function which is given to me as a black box or oracle. So I can press a button, send in some input, and then it will give me the function value f of x. So let me use this shade to represent that I don't need to know what's inside it. I just need to know the interface. I send in x, it will give me f of x. And then the goal here is to learn something about f. For example, a typical example you might have seen before is, I give you a box which encodes a polynomial with degree d. So it has d plus 1 coefficients you want to figure out, right? So how many times you have to query this box in order to figure out this polynomial? Well, this is the famous polynomial interpolation problem. So this is just one example, right? Now, we have the classical black box. And in the quantum setting, how should we define a quantum black box? Well, you might be saying, okay, how about we just say you can send in any basic state or even in superposition, and then I give you kate f of x. Does this work? Do you see a problem? This is not going to be unitary, right? So for example, if f is constant, then every time you send in anything, you get the same output. So we want to keep the operation unitary. So that's why we cook up a unitary implementation of a function. I denote it as U sub f. So I'm going to introduce another register. So the top one will be the input register, and the bottom one, you can call it the output register. So what happens is, instead of computing f of x on the input register directly, I'm going to compute the function and then XOR this function value to the output register. Huh. That's epic. It's really embarrassing, right? For us working in cryptography and security, that we cannot get rid of this at all. Okay, so let me highlight. This is going to be the unitary implementation of a function. So we compute f of x and XOR to the output register. And in fact, we can also query this in superposition. So you can send in a superposition over x here, and even superposition over y. But usually, you probably don't want to do it unless your adversary wants to attack something. Okay. So for simplicity, you can just think of this unitary function as a gate, right? You can use this as a gate in designing a quantum circuit. So when we in this model, when we want to compute something, we only care about the number of queries that we make to this black box. Right? So time efficiency is preferred, although not required. But we'll see most of the algorithms we'll discuss, they actually are time efficient. But that's not a top priority for now. Okay? So you might be wondering, why do we move to this black box model, this query model? Well, for one, this is a very clean model. We can actually design and analyze algorithms, and oftentimes we can prove very tight bounds, which is otherwise impossible in a plain model. And also sometimes we can turn this black box setting into an algorithm that solves real-world problems. And we'll see some examples later on. Okay, so let me get to the very first problem, or quantum algorithm, which is due to Deutsch. So here, we're given a function which is pretty simple, 1 bit to 1 bit. Right? And then, for such a function, there are only 4 possibilities. I can actually exhaust the truth table here. 4 possible functions. And you can see these 2 functions, the first 2 functions, they are constant, meaning the outputs, they're the same regardless of the input. And the last 2, you have exactly 1 input to map to 0, 1 input to map to 1. So we call these 2 functions balanced. All right? So the problem here is we are given this some function as a black box, and we want to figure out whether this function is constant or balanced. So how do you solve this classically? Well, you just ask the input on 0 and 1, and then you can compare the outputs. Right? So 2 queries are definitely sufficient, but you can immediately convince yourself 2 queries are also necessary, because without querying one of them, you would never know if the outputs will be the same or not. So classical 2 queries are both necessary and sufficient. And I want to show you that with quantum computer, we can solve it with just 1 query. And here is the quantum algorithm, the very first quantum algorithm we're going to see. Okay, so it just uses 2 qubits, initialize them in K0 and K1, and then apply Hadamard on both of them, and then make a query to the black box function, the unitary implementation of the black box function. And after that, apply Hadamard to the first qubit, and then measure. And we'll see that this measurement outcome will be F0 XOR with F1. And this is enough information to tell us if the function is constant or balanced, right? Because if it's constant, then this XOR is 0. If it's balanced, then it's 1. So we can perfectly tell which case it is. So this is a quantum algorithm. It uses 1, 2, 3, 4 gates plus this unitary implementation of the function. Yeah, I think we have time to actually analyze this quantum circuit. Oh, actually, let me ask the audience, how many of you will be angry if I actually spend time to analyze this algorithm step by step? Okay, all right, good. Let's do it. So how do we analyze a quantum circuit? Well, we basically just follow the time step and see how the quantum states evolve. So let me give some kind of time stamps. So call this 1, 2, 3. Okay. All right, let's go. So the initial state, K0, K1, right? And then we are going to apply Hadamard on both. So it's Hadamard on qubit 1, Hadamard on qubit 2. And what will happen? Well, from what we discussed before, K0 becomes K plus, K1 becomes K minus. And let me just write it out. So this is K0 tensor with K0 minus K1, and K1 tensor with K0 minus K1. Okay. Are we good for this step? Yeah, again, I'm ignoring the normalization factor. You can figure it out in the end most of the time. Okay, now, second step, we're going to query this unitary function, the black box function. So by linearity, what happens is, so let me just highlight. That means we're going to evaluate f on either 0 and 1, and then XOR to the output register. So we have K0, and then 0 plus f of 0, minus 1 plus f of 0. Okay, and then the second term, we compute f of 1 and XOR it to both components here. All right, nothing surprising so far. Now I'm going to just manipulate this expression a little bit. So for the first term, I'm going to pull out this sign, which is -1 to f of 0. Okay, actually, let me finish writing it, and then we can convince ourselves this is correct. So I claim that I can rewrite these two terms by pulling out some sign and then we're left with just the simple Ket0 minus Ket1. And basically what I'm using here, is a simple identity, which is for any z here, you can pull out -1 to the z and left with Ket0 minus Ket1. So you can verify this identity. So that's what we used here. Okay, now we can combine terms because these are just phases, like complex numbers. You can put it around anywhere. So we can combine these two terms and get -1 to the f of 0, K0, plus -1 to the f of 1, Ket1. That's what we have on the first qubit, and the second qubit is K0 minus Ket1. So a side note, something interesting here is that this second qubit, you can see, it actually doesn't change. So this is what sometimes people call the phase kickback trick. Basically, if you have some input bit b, and then Ket minus, and then you query this function. Basically, we're just going to compute the function into the phase, and doesn't change this output register. So this is the phase kickback trick. Anyways, so let's observe this state here. Again, this is the state right here after step 2. Okay, so what we're going to do next is apply Hadamard to the first qubit. So apply Hadamard. That means identity to the other one, but that doesn't matter. Let's just focus on the first qubit. So we want to apply Hadamard to this one. Do you recognize what that will be? That's exactly. So that's going to be f0 plus f1. Okay? So because if they're the same, let's say they're both 0, then you have Ket plus. So Hadamard brings you back to 0. If they're not the same, say this is 1, this is 0, this is 1, then we have Ket0 minus Ket1. That's minus. Under Hadamard, we get back to Ket1. So in either case, we get exactly f0 plus f1. And that's exactly what we need to determine the two cases. You're asking the second qubit. Yeah, I didn't write it down because it doesn't matter anymore. Because all the information is already encoded into the first qubit. And we can extract this critical information from it. So that means if we measure next, we'll get exactly this bit. Okay? So this shows some speed up, right? Quantum computer can save one query. Maybe that's not so eventful. But let me just mention there's a generalization of Deutsch algorithm. Okay, maybe I can define the problem. So there's a generalization called Deutsch-Josza algorithm. So here, we consider an algorithm, a function from n bit to 1 bit. And then we have the promise that either f is constant, meaning all outputs are the same, or it's balanced, meaning there's exactly the same number of inputs which gets mapped to 0 or 1. You can divide your input domain in two halves, two equal halves. So this is a promise because not all functions are, either constant or balanced. They can be more arbitrary. But we are promised this function is one of the two cases, and the goal is to decide which case it is. And it turns out, you can convince yourself, classically, at least in terms of deterministic algorithm, we need basically 2 to the n over 2 plus 1 queries. You have to query half of the input domain plus 1 to see if they're all the same or you see some different output value. Right? But then there's a quantum algorithm which can solve this problem, again, in just one query. And that's the Deutsch-Josza algorithm. And the algorithm proceeds pretty much like the Deutsch algorithm. Let me just write down the quantum circuit. So I'm going to start with n qubits initialized in 0. And then just one additional qubit, which is going to be the output register, initialized in Ket 1. Then I'm going to apply Hadamard to all of them. And then query this unitary function u sub f. So again, this is the black box implementing f as a unitary. And afterwards, I ignore the final qubit. Well, what should I do here on the top n qubit? We don't have many options. Just apply Hadamard. And then I measure. Okay, so if you analyze this circuit, we will see that this measurement outcome will be the all zero string if and only if f is constant. So this gives us a way to distinguish the two cases by just one quantum query. Okay, so are we happy with this algorithm here? It shows classically you need 2 to the n over 2 queries. Maybe I can write it down. And quantum, you just need one query. I think this is pretty remarkable. I'll be very happy to just stop here. But did you notice something that's not so satisfying? So when I say classically we need 2 to the n over 2 plus 1 queries, do you agree with me?
Most of the time you do a lot less, right?
Oh, say it again?
Well, you'll be spending a lot of time trying to, if a function is not constant, right? Your operator will be spending an enormous amount of time trying to find that two places which are apart.
Exactly.
Most of the time you'll find it quickly, right?
Yeah, so that means, what if we use randomization? We pick a few, randomly pick a few inputs and see their output. Then if they're constant, if the function was constant, then it's always going to be the same output. But if it's balanced, well, then each time with half probability, you'll be in a different fiber of the function. So, we don't need many samples in order to see two different outputs. And you can, by just a little bit more analysis, in fact, with just linear number of queries, n queries, we're going to be able to tell the two cases, at least with overwhelming high probability. But still, it's not going to be perfect. This randomized process, you're still going to be make mistakes sometimes. And this quantum algorithm, it never introduces any errors. So that's another advantage, So now we have a linear versus constant speed up, and also, this error advantage. But maybe we're still not satisfied with this speed up. Okay? And I do have something prepared for you.
Can I ask one quick question?
Yeah, sure.
I'm curious, in the Deutsch-Josza algorithm, what do you actually end up computing? Because you're not computing the XOR of that one.
No.
So what do you actually end up computing?
Well, this will become, I think, more evident in the next algorithm. So basically, by observing the samples, this is basically sampling from the Fourier domain. If we jump ahead, and this tells us something about the function. So for example, here, the only thing we're going to see is zero, the all zero string, if the function is constant. If it's a balanced function, then it's going to be some other string. So this is a way to.
Is it like a dot product with an independent vector?
You're ahead of me. That's Simon's algorithm, which we'll discuss in a moment. Yeah. So, okay, without further ado, let's get to it. So this linear speedup maybe is not super exciting. We can do better. So let me introduce this problem here. This is due to Simon. So again, we're given a black box F from n bits to n bits. And the promise here is a little bit peculiar, right? So we assume there's a secret string S, which is non-zero, such that for any inputs x and y, their function values will be the same if and only if they are kind of shifted by S. So XOR S is Y. This is the promise on the function. So the function, visually you can think of it as I divide it into these rows. In each row I have one string, and then the other one is going to be masking the string with S. So the function will map each row to the same value. So this is going to be F0, F1. But across different rows, the function values are distinct. Okay, so this is the function given to us, and the goal, as you have imagined, we want to find S. We want to find this secret string. Okay, now let's talk about how to solve this by a classical algorithm. Just very quick, get some idea. If it's a deterministic algorithm, then as before, in the worst case, we have to query one more than half of the input domain. So it's 2 to the n-1 plus 1. And if you are willing to use randomized algorithms, we can do better. Because essentially this problem here, what will be sufficient for us to figure out S? We just need to see a collision, which is a pair of inputs that have the same function value. And then if this happens, we know X XOR Y is going to be the secret. So we just need to find the collision. Then the question is, what's the cost of finding a collision? Well, this alludes to the famous birthday bond. So essentially, we need square root of the input domain size. So that's square root 2 to the n, or 2 to the n over 2. And you can also show this is optimal classically. So any randomized algorithm, we need to spend square root 2 to the n many queries. We cannot do better. Now, here comes the exciting part. There's a quantum algorithm that can find S in linear number of queries, big O of n. And that's Simon's algorithm. So let me introduce you the algorithm, and then I think we can take a break. So while I'm writing down the algorithm, I want you to appreciate, this is going to be an exponential speed up. So Simon's algorithm actually has a simple two-step structure. So in the first step, we're going to run a quantum sampling procedure. A bunch of times. So each time we're going to get a string of n bits. So let me denote them y1 to yk. And then second step is going to be purely classical, a classical post-processing. Then can figure out the secret S from these k samples. And in this particular case, we just need to solve a linear system of equations. And it turns out the number of samples we need just need to be linear. So big O of n samples will suffice. All right. So this is the algorithm. But obviously, the most essential part is the quantum sampling subroutine. So let me show you that subroutine. So let me set it up. And actually, I think everybody at this moment would be able to design this quantum subroutine. So let me just initialize these two registers, 0 to the n and 0 to the n. And what would you do? Maybe I can remind you the previous two algorithms to give you some hints. Give you some inspiration. So what kind of quantum circuit you can think of? What should I apply to the top n qubits? Hadamard, right? We don't have many options. So I just apply Hadamard. That's a fancy Hadamard. I didn't expect that. So let me just use the shorthand notation, Hadamard tensor n. So in fact, I use this slash to represent there are actually multiple wires stacked together. So we apply Hadamard to each of the wires, to each qubit. Okay, that's good start. And then, well, the natural choice is to query this unitary function. And what do you want to do next? This is not a trick question. Really the first thing you can think of. Another hint, what we did before. Just, do Hadamard again. And that's all. And then I measure. This gives me a classical string of n bits. Okay, so this is the sampling subroutine. And we're going to run this n times, or some constant factor of n times. And that will be sufficient information for us to extract S. Yeah, so I think this is a good time to stop. And
How is it different each time? It looks like the same.
Well, when we analyze this in the next lecture, every time this is going to be a random sampling procedure. So every time this output y here is going to be a random sample from some distribution. And we'll see what that distribution is and how that helps us solve or find S. Okay, and that's a very good question. And then we'll resolve that in the coming lecture. So I think we have a break for half an hour. So we'll resume at 11. Thank you.